In this section, we are going to talk about the MPLS Fundamentals. Let's start with the MPLS overview. Multi-protocol label switching (MPLS) is a packet forwarding method that makes forwarding decisions based on labels instead of on the layer 3 destination of the packet. MPLS was designed to support many different layer 3 protocols, but in this section we focus on IP only. Before we dive into MPLS, let's be clear that with today's routers, MPLS is not much faster than traditional IP routing guys. So why would you even consider MPLS? Well, MPLS decreases the forwarding overhead on core routers, making them more efficient. In addition, MPLS can forward other layer 3 protocols besides IPv4, and MPLS supports multiple services such as unicast routing, multicast routing, VPNs, traffic engineering, QoS, and something more. Therefore, guys, MPLS is really efficient and really flexible. Let's take a look to the MPLS lib and MPLS lfib. On the screen, notice that the control plane of the MPLS-enabled router is responsible for exchanging labels with other MPLS-enabled routers and using a label distribution protocol in addition to exchanging routing information using routing protocols to populate the IP routing table, which is RIP. Once labels have been exchanged, the label information is used to populate the lib, and then the best label information can be used to populate the forwarding information base, which is fib, so unlabeled packets can be labeled, and the lfib, so labeled packets can be forwarded or labels can be removed when packets need to be forwarded by the fib. So yeah, it might look a little bit confusing, and let me tell you more about this one. Let's say an unlabeled IP packet arrives with a destination of 10.0.0.5. Because it is unlabeled, the fib is used to make a forwarding decision. If the fib indicates that the outgoing interface is not an MPLS-enabled interface, the packet is forwarded unlabeled, guys. If the fib indicates that the outgoing interface is an MPLS-enabled interface, a label is added to packet and the labeled packet is forwarded, labeled out the MPLS interface. Let's say a labeled packet arrives on an MPLS-enabled interface. Because it is labeled, the lfib is used to make a forwarding decision this time. If the lfib indicates that the outgoing interface is an MPLS-enabled interface, the label is removed, a new label is added, and the labeled packet is forwarded out the MPLS interface labeled. If the lfib indicates that the outgoing interface is not an MPLS-enabled interface this time, the label is removed and the unlabeled packet is forwarded unlabeled using the information in the fib. Let's go ahead with the label switching routers, LSRs. So, routers R1 through router 5 are part of the MPLS domain in the screen you can see in here. So they are known as label switching routers because they support MPLS. They understand MPLS labels and can receive and transmit labeled packets on their interfaces. In this case, guys, router 1 and the router 5, these two guys in here and router 5 is in here, are considered as the edge LSRs, and router 2, router 3 and router 4 are named as intermediate LSRs. An edge LSR sits at the edge of the MPLS domain and adds labels to packets that are entering the MPLS domain, removes labels from packets that will be leaving the MPLS domain, and even forwards packets as needed based on labels or the lack of a label. An intermediate LSR sits within the MPLS domain and primarily forwards packets using label information. And let's go ahead with the label switched path term. The label switched path, LSP, is the cumulative labeled path that a labeled packet takes through the MPLS domain. It is a unidirectional path, and you can see on the screen, therefore, in a complex network with multiple potential paths between source and destination, it is possible that the LSP from source to destination could be different from the LSP that is used for the return traffic. However, typically same path in reverse is used for the return traffic because of the underlying dynamic routing protocols such as OSPF and EIGRP that are used to build the symmetrical network and its forwarding paths. In this case, the LSP from router 1 to 10.0.0/24 uses labels like 87, 11, 65, and 23. Along the path, each router examines the label to make a forwarding decision, removes the label, adds a new label if required, and then forwards the packet. For MPLS to work, a label needs to be added to packet, as I explained to you previously. The label is added between the layer 2 frame header and the layer 3 packet header. The label is 4 bytes, which is 32 bits in size, and contains 4 different fields. You can see on the screen about the fields, and the first 20 bits label define the label number. The next 3 bits EXP are used for quality of service. The 1 bit S field is used to define whether the label is the last label in the stack when more than one label is used in the packet, for example with MPLS VPNs, and the final 8 bits TTL is just used like IP's TTL so that MPLS frames are discarded if they have not reached the destination by the time the TTL reaches to 0. So MPLS-enabled routers automatically assign labels to every network that they know about, guys. How does a router know about a network? It can be locally configured by configuring an IP address on a router interface and issuing the no-shutdown command, as you know. And it may also know through the propagation of routing information with dynamic routing protocols such as OSPF and EIGRP. For example, on the screen you can see that router 5 this router in here gave a label of 23 for the network 10.0.0.0/24. But router 4 labeled the same network with 65, router 3 labeled with 11, router 2 labeled with 87, and router 1 labeled with 19. What should you notice from this is the local significance of the labels, guys. Each router, regardless of whether it is locally connected to network 10.0.0.0/24 like router 5 or not locally connected like the other routers, generates a local label for the network it knows about regardless of how it learned it about. So let's go ahead with the label switching. Based on the information found in the IP routing table and the lib, the routers on the screen have populated their LFIB and FIB as shown. Okay, you can see the populated LFIBs and the populated FIBs. Now, when router 1 receives a packet with the label 19, it examines the LFIB and notices that it must forward it with the label 87 to router 2, right? However, in this case, if packet is coming in the interface that is connected to the 192.168.0.0/24 network, it doesn't have a label as there are no routers imposing labels on packets out that interface. Therefore, when the packet arrives on the interface connected to 192 network of router 1 with a destination IP address in the packet for 10.0.0.0/24, the FIB indicates that label 87 has to be added and the packet needs to be forwarded with R2 as the next hop address. When router 2 receives the packet with label 87, it examines the LFIB and notices that it must forward it with the label 11 and R3 as the next hop address, as you can see in here, and R3 via. Then what happens? The packet is reaching to router 3 then. When router 3 receives the packet with label 11, then it also checks the LFIB and labels out with 65 via router 4, and router 4 gets the packet and it labels it with 23 and forwards via router 5. When packet comes to the router 5, it examines the LFIB and notices that there is no outgoing label in here, which means it is the end of the LSP and therefore the label must be removed and normal routing has to occur with the IP routing table, which is FIB.